All right, Jack, what number are you asking about specifically?
Number 6.
6. Okay. All right. So -3. Now, here's how I'm going to do this, okay? I will graph -3 to the x. And then I'm going to do +1, okay? So A equals -1. B equals 3. H equals -1. And K equals 0. Okay? Now we are going to have a horizontal asymptote, henceforth symbolized by HA, a horizontal asymptote of y equals k. In this case, it will be y equals 0. Okay? And so as we do the graphing, then we're going to, put this stuff on here. Okay. So, what are we going to do first? So we're going to make a table. I'm going to make this a horizontal t-table where we got x and y. And I'll do -3, -2, -1, 0, 1, 2, and 3. Now, I'm doing negative and positive values because the domain of all exponential functions is all reals, no restrictions. Okay, so I want to make, God bless you, I want to do some negative numbers and positive numbers. Okay, all right. So, 3 to the -3 is 1 over 27, right? And then it's going to be hitting with the negative sign, so we got -1 over 27, -1 over 9, -1 over 3, -3, I'm sorry, -1, excuse me, -3, -9, -27. Okay? All right. So we'll graph the points, and then I'm going to use a different color, and I'll graph the points in which I have adjusted for h equals -1. Okay? So here's my tick marks. Oops. So here's 1, 2, 3, 7. Okay. So -3, -1/27. Well, that's like there. -1/9. That's like that. -1 is -1/3. That's a little bit easier to graph. 0 is -1. Okay. 1 is -3, and that's about all I can get onto my graph here. I can scroll down a little bit and continue it further. Down here, 1, 2, 3. And then for 2 it'll be -9. 1, 2, 3, 4, 5, 6, 7, 8. So down. Let's call it down here somewhere. Okay. Now so this is -3 to the x. Now I'm going to adjust it for -1. Now you could have done -1 at first right away. That's fine. Okay. I'm going to change the color. So now I'm red. And all that's going to happen is each one of my points is going to be adjusted over one square. Okay, okay. Okay, so like this. And so here's your graph. Now notice the domain doesn't change. The range A is less than 0. Therefore, you guys know the symbol for therefore? It's 3 dots. That means therefore. Just so you. I mean, you guys are into emoticons, right? And all this little, you know, OMG and all this other stuff. Well, the 3 dots, okay? That's how the mathematicians have been, you know, doing stuff like this for a long time, you know? We're way ahead of you guys. Okay, therefore, the range is, it's all real such that y is less than k, which is y is less than 0. Okay? So there you go. All right? Now, you want to make the adjustment with h ahead of time. That's fine. That's up to you. Okay? Did this help? Jack, did this help?
Yeah.
Okay. All right. Now, let's move along here. What's the ugliest one? 7. 7 ain't too great. Because, let's look at 7. Because 7 has h and k. So let's do h and k. All right? Let's do 7. Let's roll on down, and let's do 7. And so let's analyze it. A is 1. Here, let me go back to black. B is 2. H is 2. And k is -3. Therefore, we have HA is y equals -3. We have a horizontal asymptote at -3. Now, we're going to graph that. We're going to put that on the graph right away. Okay? All right. So we're going to let's make ourselves a little table here. So I'm going to graph y equals 2 to the x. And then I'm going to throw in h and k. Okay? So I got x and y. And this is going to be really slow. -3, -2, -1, 0, 1, 2, 3. I throw in these guys here. And, I mean, this is like the billionth time we've been through this, right? So this is 1/8, 1/4, 1/2, 1, 2, 4, and 8, right? Okay. Domain, all reals, range. Okay, A is greater than 1, so the range is y is greater than -3. Okay, everybody good so far? Okay, all right. So now we can make our graph. Okay, first I'm going to just make the graph of y equals 2 to the x. That's going to look like this. 1, 2, 3, 1, 2. Okay, so -3 is -1/8, 1/8, 1/4, -1 is 1/2, 0 is 1, 1 is 2, 2 is 1, 2, 3, 4, and 3 is 8, which is up there somewhere. Let's just do these, okay? Now, my short-term memory is not so great. Okay, 2, -3. So h equals 2k equals -3. So that's our adjustment. So each one of these points here that I plotted, I'm going to move 2 to the right and down 3. Okay? So let's use red. So this first point. 2 to the right, 1, 2, and then 1, 2, 3. There's my first point. Second point. 2 to the right and down 3. This is when I have the hardest time with 1, 2, so it's like a little bit. And then 2 to the right and down 3, like that. That's one's a little bit too high, that should be more like that. So, okay. All right. 2 to the right and down 3. 2 to the right, 1, 2, 3. 2 to the right, down 3. 2 to the right, and down 3. Okay. These are in the wrong place, so here's the graph going like that. Okay. All right. What do you think? Any questions? Now, I'm not going to make you, we're you know, I'd like you to be able to do this probably with these type of problems, I'm going to make you just identify the domain and range. Oh, let's put in, here is the asymptote, right here. Y equals -3. So that's a good thing to put in first, okay? So you're going to approach this line but never reach it. Okay? Any questions about the domain, the range, the asymptotes, any of that stuff? Okay, you feel like you got it? Yes.
Can we do another example?
I'll do as many as you want. Okay, and then we'll go to the homework and we're going to do that. Graphing's hard. It's hard. When you guys got your quizzes back, that's where the most mistakes were. They were on the graphs. You know, I didn't do a good job of, you know, inflicting enough pain on you, you know. Yes?
Would the domain be all real numbers?
The domain's all real numbers. Did I say it wasn't that? What did I say? Yeah, I said it was all real. What? Giving me a hard time? No, the domain's all real numbers. For all exponential functions, the domain's going to be all real numbers. Okay, Margot?
I'm just trying to, oh, never mind.
Okay. All right, let's do another one. What's the next most awful looking one? Oh! Now what's this? Oh, okay, let's do 8. 8 looks pretty awful, doesn't it? Does it look sufficiently awful? All right. But you get the hang of this. It's really so. All right, let's break it down. So A is -2. B is 3. H is -1. And K is 2. Okay, so don't let the parenthesis throw you. Okay? You know, the exponent would execute first before you hit it with the -2. The parentheses are superfluous. They're there to confuse you. Okay? Or to test you, I should say. So we have a horizontal asymptote at y equals 2. All right? The domain, God bless you, is all reals. Okay, the domain is unaffected by h. But the range, what's the range? What's the range? Anthony.
Y is less than or equal to 2.
Okay, you're very close. Okay? It definitely has to do with k. But we have an asymptote. Okay, we have a horizontal. What does an asymptote mean? You're going to approach it but never reach it, right? Okay, so what's the range? You need to modify your range just slightly. There you go. Very good, but you got the direction right. Okay, because you analyzed A properly. Okay, the range, all reals such that y is less than 2. Okay? All right, so I'm going to graph. I will graph y equals -2 times 3 to the x. That's what I'll graph first. And then I will adjust it for h and k. All right? So, we make our little table. X and y. Now, we've been through this before. We can reuse all this stuff. So, -3, -2, -1, 0, 1, 2, and 3. Okay, so we got 1 over 27 times -2, so we got -1 over 54. Okay, we're not going to graph that. That's ridiculous. You can't even see it. Okay, that's smaller than the tip of my pen. All right, then we got -1 over 27, -1 over over 9, right? What am I doing? 18. -1 over 9. Okay. -2. Oh, wait a minute. Okay, -1 is 1 over 3 times -2. calculator. Sorry, guys. I should be using a calculator. All right. Negative 3 is 1 over 27 times negative 2. It's negative 2 over 27. Negative 2 over 9. Negative 2 over 3. Negative 2 over 1. Negative 6. And negative 18. And negative 54. Okay, you guys agree? Okay, so I'm doing negative 2 times 1 over 27, negative 2 over 27, negative 2 times 1 over 9, negative 2 over 9, negative 2 times 1 over 3, so that should be negative 2 over 3, negative 2 times 1, that's negative 2, negative 2 times 3, negative 6, negative 2 times 9, negative 18, negative 2 times 27, negative 54. Okay? All right. How much of these points we can actually, well, let's see what we can do here. I'll put this here. Everything's negative. So, 1, 2, 3. Negative 2 over 27. That's like way up here. Okay? Negative 2 over 9, that's almost a third. Okay, so that's going to be around here. Negative 2/3, that's about here. Now we're jumping to negative 2 at 0. Yeah. And at 1, we're at negative 6. 1, 2, 3, 4, 5, 6. All right, that's about all we can show. Okay, after that, we're like off the charts. Okay, now H, well, I got H and K right here. H is negative 1 and K is 2. So, each point is going to be shifted 1 to the left and down 2. Okay? So I go 1 to the left and down 2. It's going to be just about right there. Come on. Okay? 1 to the left and down 2. 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 Okay, and so here it is. Okay? And here is no, I screwed up. I misread the, I should have gone up. I did this yesterday. 1 to the left and up 2. Should be up here. 1 to the left and up 2. 1 to the left and up 2. 1 to the left and up 2. And finally, 1 to the left and up 2. And here is the asymptote. And here it is. My mistake. All right, coming back like that. Just misread. You know, I looked right at it and I saw it, K is negative 2. But I realized my mistake when I thought about the asymptote. It's not approaching the asymptote, it's approaching negative 2. How many saw that? I was making a mistake. What?
I saw it at the end. That's okay.
Okay, all right. You know, it's like the emperor's new clothes. In case you see me doing something wrong, feel free to holler. Okay. All right. What do you want to do next? Do you think you can do 9? How do you feel about 9? Feel good about 9, or should we do it?
Yeah, let's do it.
Let's do it.
Do it.
Do it. Let's do 9. Oh, it's a fraction. Okay. Yeah. Fractions. Okay. Forgot about that. Okay. A so this number 9. 9. A is 1, B is 3/2, H is 0, K is -2. We have a horizontal asymptote, Y equals -2. Domain, it's all real numbers, okay? Range, Y is greater than -2. Okay, everybody good so far? We got the asymptote, we got the domain, then we got the range, we broke down the letters. Okay, we make the table. Now I'm just going to do 3/2 x. So -3, -2, -1, 0, 1, 2, 3. Okay, 3/2 to the -3rd. 27 over, I'm sorry, 8 over 27. To the -1/2, 4 over 9. To the -1, 2/3. To the 0, 1. To the first, 3/2. Second, 9/4. Third, 27 over 8. Now, these numbers are actually pretty easy to graph. Okay? You're not gonna, you just approximate them. 8 over 27, that's a third. Okay? 4 over 9, that's a half. 2/3, 2/3. 1. You follow me? 3/2 is 1 1/2. These are, don't freak out because they're fractions. 9/4, that's about 2. Okay? 27 over 8, that's about 3. You guys follow me? You're graphing. Okay? So, it's never exact. But you're presenting a picture of what the function is doing and showing the trend properly. That's what's most important. Okay? So use your common sense in terms of graphing this thing. This is going to be a pretty easy thing to graph. Now, our asymptote is at -2, so we're going to have that adjustment. So we're not going to move to the right or left, but we'll shift every point down. But first we'll graph these. Here, I got to put it up. I'll go the other way. Put it down here. Because everything's positive. Put the -2 in here. Okay. All right. So -3. 1, 2, 3. It's about a third. Right here. Okay, -2. It's a half. See, that graphs pretty easily on the graph paper. Okay, -1 is 2/3, right about here. 0 is 1, and 1 is 1 1/2, and 2, we'll call it 2. 1, 2. And 3, we'll call it 3. 1, 2, 3. We can put a lot more points in here because it grows slowly. Okay? We could put in 4. Okay? What would 4 be? 4 would be 81 over what? 16, which is a little over 4, right? Yeah, 4, a little over 4. 4 times 16, 32, 64. Oh, you're saying 5? Oh, yeah, 5. Yeah, you're right. 5 exactly. 1, 2, 3, 4. 1, 2, 3, 4. Very good. You guys are good. Okay. So we got a 9. This is pretty good. Okay, we got some nice points here. Okay. So don't freak. Fractions actually are pretty easy when you're growing them exponentially. Okay, they're not hard to work with. Okay. All right. Now every point is simply going to get moved down 2. That's it. And let's put in the asymptote. Okay. So this guy goes down 2. This guy goes down 2. This guy goes down 2. He goes down 2. Okay, 1, 2, right here. 1, 2, 1, 2, 1, 2. Okay. Okay. All right, not too bad. Not too bad, right? Okay. All right, that was 9. We got any more of these fraction guys? That was 3 halves, right? Let's see. Okay, let's do, I haven't talked about compound interest, and so let's do that. I really, seriously don't like compound interest problems. I just think they're just really extremely boring. But you have to do them, and they always bring them up. And it's like exponential functions. They describe how the world works. Like you can understand life and the history of the universe and all these other things. And what do we talk about? Compound interest. Like give me a break. Anyway, well, we're talking about compound interest. Well, money's important. Makes the world go round. All right, so you got $3,500. Now, okay, I haven't given you the formula for compound interest. Maybe you guys worked on it on your own. Let me give you the formula. Let me put this back here. All right, so the amount of money you have, this is simple interest, equals the principal times the rate of interest times the number of years that the rate of interest is applied. And that's simple interest, okay? So you get 5% a year, okay? So the amount of money you're going to get is going to equal the principal times 1.05 raised to the power 1.05. And let's say you put the money in, now 5%, what am I talking about? We haven't had 5% for like ages. Try 0.02% or something like that. That's about what you're getting now for 10 years. Okay, interest rates are ridiculously low. All right, now, they do this thing called compounding interest, which is going to kind of like fool you when you get any more money. Now, here's how it works. The amount of money you have equals the principal times 1 plus the rate of interest divided by the number, God bless you, divided by the number of times it's compounded, raised to the power of the number of times it's compounded, times the number of years. Okay, now you can program this in your calculator or whatever, maybe some of you already have. Okay, all right. So, anyway, the idea is that you think you're getting more money because your rate of interest is getting compounded. So what happens is suppose it was 4%. Instead of giving you 4% at the end of the year, taking your principal multiplied by 4% and then adding back into your amount of money, they give you 1% every quarter and then add that in. So you're growing a little bit faster. So, let's look at this problem here. I'm going to make this a little bit smaller. You got it on your sheet so you can see it all right. Then I'll make it bigger again. Okay, you deposit $3,500. So P equals 3,500. The interest, 2.5%. There's a joke. Okay, but make sure you put it in the proper decimal form, 0.025. Okay, now find the balance after 1 year if it's compounded with a given frequency. Now, 1 year, okay, quarterly, or monthly. Okay, now let's use this compound interest formula in each case so you get used to using it. So, in other words, if you get it once a year, n equals 1. The number of times it's compounded is 1 time. So the amount of money you're going to have is going to equal the principal, $3,500 times 1 plus 0.025 divided by 1 raised to the power of, after how many years? How many years? After 1 year. Okay. Oh, and t equals 1 year. Okay, to the first power. Okay. So in other words, it's simply going to be $3,500 times 1.025 to the first power. Okay? That's simple, and that's what's called simple interest. Okay? And you can just put that in the old calculator and get out your answer. Okay? Now, you compound it quarterly. Okay? So, same R, but now n equals 4 if quarterly, right? Quarterly means 4 times a year. So your principal will equal 3,500 times 1 plus 0.025 divided by 4 raised to the power of 4 times the number of years. Well, in this case, it's just 1 year. So it's just going to be 4 times 1. Okay? And I think you have a thing in your calculator for compound. I don't know if you have it in there or not. You can look. You guys are, a lot of times you're way ahead of me. I'm always doing things like, just putting stuff in or whatever. Anyway, but I'm going to show you, let's just do this in using the workspace to do this. All right, so it's 3,500, open parenthesis, 1 plus 0.025 divided by 4, close parenthesis, exponent, little up arrow there, 4. Now, suppose you were going to do it for more than 1 year, then that exponent would have to be in parentheses. Okay? Everybody got this down? I want to collect these. Anthony, you still with us, sir? Okay. All right. Don't feel late. Okay. All right. So, and whatever, let's see what that is. All right. Now, let's compare that to just simple interest. Okay? So we're going to do 3,500 times 1.025. Okay? You got a whole extra, like, not even $1. Okay? About 80 cents more. Okay? All right. Now, suppose we did it 12 times a year. Maybe that'll be better. Think we'll get more money? Think it'll be a lot more money if we do it 12 times a year? What do you think? Okay, a little bit is right. So let's do a second and enter, and second and enter, and let's change this to a 12. So we're going to compound 12 times a year, and then up arrow, and we're going to make this 12. Okay, it went up to, the difference between quarterly and monthly is about 18 cents. Now suppose we did it every day. What do you think that would do for us? Every day. Yeah.
Would it make like the amount of just like very, very, very small?
Let's try it. Okay, so let's do a second, enter. Let's try it every day. 6, let's do 365. Okay, close up arrow. 365. Yeah. The difference is about 9 cents if you do it every day. Okay, so what's going to happen is you eventually reach a limit on how much your money is growing. As n increases, you're going to reach a fixed. It's not going to grow to infinity. It will level off. Okay? And the base number for its leveling off is a really important number in mathematics. All right. Anyway, so that's that first problem. Yes?
So I know that in the equations he means like time as in like how many
Number of years.
Then n
Is the number of times compounded in 1 year. Okay? All right. Okay. Now, here's an example of something that really makes me mad. In exercise 13 and 15, we have a population model, 1990 to 2000. They have an equation that they put together where the population equals 29,816,591. Okay. A is 29,000. 816,591. B is 1.0128. Okay? So A is the starting point, so that's population for the first year. So the population in 1990 is 29 million, blah, blah, blah. Okay, the growth factor is 1.0128, and the percent increase is 0.0128. Okay, you guys see the difference? The growth factor is B, and the percent of increase is B minus 1. Okay, that's how much you're going up every year. All right. Now, estimate the population in 2007. Well, you would just put in 7 for T, but if you did that, you would be a really bad person. Okay? Now, you're going to have to do it in a test or something. Does anybody know why you would be a really bad mathematician if you did that? Anybody know why? Even though the book tells you to do it and trains you how to do it? Any idea? Yes? Okay. The data is collected from 1990 to when? 2000. Okay. Now, what are they asking? And you developed a model based on those years, right? So what's the domain of your model? Now, no. I want you to think, don't think in terms mathematically. Now, I want you to think in terms of your data. In other words, your data has a domain. What is it? No. That's your starting point. What's the domain? Yeah. Okay, your data has a domain. That's 1990 to 2000. Okay? And that domain makes the model. Okay? Now, a model should never be used outside of its domain. Ever. Okay, this is one of the fundamental laws of statistics. Okay? What they're asking you to do is called extrapolation. They're asking you to take a model that was developed between 1990 and 2000 and apply it 7 years outside of its domain. That is a completely and totally wrong thing to do. And I'm not saying if they ask you in a quick test to do it, do it. Okay? But statistically, it's a mortal sin. Literally. Well, I mean, it's exactly. You won't go to hell if you do this. Okay? But you'll make some serious mistakes. Now, why is that? You need to think for a minute. Why would that be a bad idea to do that? Yeah?
The exponential growth will probably change.
It's always changing. Things are always changing. Let's think about exponential growth. It's always changing. Okay? And this exponent here, this number, if it's slightly off, there's huge consequences. Okay? Huge consequences. We're going to talk about that when we talk about logs. Okay? It's a slight change in a log, and boy, you got a big change in your results. Okay? All right. That's one of my pet peeves.